I'm going to talk about this again for a second. Limit laws. I showed you this last time, and you all groaned. This should be logical-ish, okay? And each of these makes sense. For instance, let's look at this one. We're saying if the limit, okay, we're saying if as x approaches a, first you can hear me, yes? Okay. If as x approaches, you're right in front of me. If as x approaches a, f approaches L, and g approaches M, okay, then you'd expect the product of f and g to approach the product of L and M, okay? There's nothing crazy here, okay? But what you have to look out for is you have to follow these rules. I see a lot of people trying to disobey the rules, and I get the temptation, and I get that it sometimes and often works, but don't break the rules. The limits have to exist, and there's also some other restrictions here, like don't divide by 0 and that kind of thing, okay? Follow the rules. Yes, ma'am? Yeah.
You know in the Mobius quiz, you have to write plus infinity.
Yes, ma'am.
Dividing by 0.
I'll try to talk about that. Good, yeah. Yeah, so again, if you're don't be dividing by 0. So the limit laws don't work that way, okay? So only use them when they work. For instance, I'm going to be talking forever about this kind of thing. So, for instance, there was something like this on the assignment. I'm going to write this in shorthand. It was something about the limit of the product. That's the product. Okay? And one of them was broken, right? F had 2 pieces or something like that. Okay? And then people are tempted to do this. You say lim, okay, it's just lim f times lim g. Okay, and then you go, okay, well that one doesn't exist, so I'll just write dne. The other one is 4, so I'll just write that, so that does not exist. I get it, I get the temptation, and honestly, sometimes it works, okay? But sometimes it doesn't work. What the heck do you do if this guy is 0? Okay, what do you do if this guy is also dne? Okay? Don't try to multiply stuff that doesn't exist. Okay? Don't try to disobey those rules. Okay? It can cause trouble. If you're desperate, sure. But if you're not desperate, you want to think clearly, do them properly, and I'll try to give you some idea of how to do them properly. Okay? Bottom line, follow the rules. Unless you're very, very desperate.
So then what would we do?
I'll tell you in a second.
Oh.
Yep. What's your question? Okay. All right. What else do I want to say? That's it for that. And again, these guys apply for one-sided limits as well, so from the left or from the right, and they also apply for limits at infinity. Not infinite limits, limits at infinity. So when x goes to infinity or when x goes to minus infinity. Okay? Okay. We did this example last time. We had a week off, so this is all just like me saying random stuff now. Okay, we had this thing. And we want the limit as h approaches 0 of this thing, right? And I said, okay, you can't use the quotient law, because if you tried to do that, you'd be dividing by 0, okay? Because the limit as h approaches 0 of h is 0. Bad. You shouldn't be doing that, okay? So we had to find another way. And what did we do? We multiplied by the conjugate radical, and we wound up with this thing. Yeah, again, if you've got all this, don't worry about it. I didn't show you that graph last time, so I figured I'd show you this time, right? Look, it's a picture with a hole in it. A hole exactly where we want the limit, conveniently. Okay? So again, what did we do? We multiplied by the conjugate radical top and bottom, we did some algebra, and we did a cancellation because the limit doesn't care about what happens at h equals 0. Okay, so we wind up with this thing. And if you graphed this guy, you'd get exactly the same thing, except that hole would be filled in, which is handy. Okay, and then after that, we used the limit laws to get whatever the limit was, 1 over 6. Okay, so we did a trick, and then we used the limit laws. We couldn't apply the limit laws directly here because of the division by 0. Good? Okay. And again, the same-ish kind of story happens when you have things like... the rest of this lesson will be clearer, I promise. When you have stuff like this. Okay, same-ish kind of thing, different method. Here you factor, right? But same-ish kind of story happens. You've got a hole. You've got to deal with this in some way that you can apply the limit laws or reasoning or something like that. Okay? Again, you couldn't apply the limit laws directly here. And same thing with that Saruman throwing the stone at the guy example. Okay? The instantaneous velocity example. Okay. Any questions about that stuff? Alright. So, in this case we had division by 0 and we solved it in these kinds of ways, yeah? We factored and canceled appropriately, and here we did the multiplying by the conjugate radical on top and bottom. Whoever asked me that question. Okay? So there's tricks that you can use. Okay. Alright, first new thing today. And following someone's remarks and my own observations, I'm going to try not to write to the right of that line. Okay. I may not actually do this one, but I'll show it to you. Okay, the limit as x approaches minus infinity of the square root of 2x squared plus who cares over, oh, bad. 3x minus 5 over the square root of 2x squared plus who cares. Okay, can we use the quotient law here? I'm going to try not to say quotient rule because that sounds like a derivative. Can we? Who says yes? No? Oh, thanks everybody. Okay, no. The limits don't exist, okay? Right? Both of these guys blow up as x goes to minus infinity, so don't try sticking in limit stuff. You don't try writing infinity over infinity or anything like that. Or minus infinity over infinity. Okay, so what do? You know what to do?
Conjugate.
See, a conjugate's helpful when you've got a square root or a radical of some sort, and then you've got, let's just say a square root, and then you've got plus or minus something else, possibly also a square root. Okay, because then all that difference of square stuff helps. What else could you do here? What did we taught? Yes, ma'am, at the back, yeah. Yeah, go ahead. There's two of you and you're collinear.
Just divide it by the highest power.
That's great. Is that? Yeah, okay, great. What's the highest power in the denominator? You're right? Okay, good. Sort of, it's x, okay? Don't go nuts over this. I think it's in the sample midterm or some of that sample stuff as well. Okay, so what do you see? What's the highest power in here? It's x squared. But the square root sort of makes the highest power look like x. So what you wind up dividing by is x, okay? So divide everybody by x. So I may get you to do some of this on your own. So you divide through by the highest power apparent in the denominator, and you do that. Okay? Then what happens? Then what do you want to do? You want to sort of bring this guy into the square root, right? So you want to get 2x squared over x squared plus x over x squared plus 1 over x squared, right? My only other comment is be careful. Sometimes there's a trap. Okay. So remember that the square root of x squared is the absolute value of x, not just x, okay? So if x is less than 0, then the square root of x squared is going to be the absolute value of x, which is minus x. Okay? So this guy is minus square root of x squared. Okay? So there's going to be a minus sign in front when you bring that x squared into the radical. Okay? That's it. The rest of it's as we've done before. Okay? Then you can simplify and use limit laws, and that's it. Okay? If you got any questions about this, let me know. Again, don't freak out, but just give it a shot. And after you do your work, you get minus, I wrote everything upside down, so I've got to be careful, minus 3 over root 2. Okay? Again, sometimes funny stuff happens. The reason you care about x negative here is that you're taking the limit as x goes that way. Okay? Because you're taking the limit as x goes that way, you've got to be careful that the square root of x squared is not x, but minus x. And so you get a minus sign there, and that's how you get this minus sign here. Okay? Okay. All right. And so the graph has what? A horizontal asymptote at y equals minus 3 over root 2. Okay? And the limit going that way is plus 3 over root 2. Again, try that out. If you got a question, let me know, but don't freak out. It's the same kind of stuff you've seen before, just clouded with the square root thing. And look, it does what we promised. And again, we can't just use the limit law straight away because what? Both those limits don't exist. Okay? If this bottom was 2x squared plus x plus 1, all to the power of 3 over 2, you'd be dividing through by x cubed. Okay? So if you had, getting sloppy, if you had something like this, okay, the highest power you see inside here is x squared, which appears from the outside as x cubed. Okay? Again, don't freak out, it's just things that turn out from time to time. Okay? Alright. Again, this is a tricky example. Questions? Alright, let's do something else. And by something else, I mean almost the same thing. Okay. Again, no comments, yeah? Questions? Anything? Again, it's a weird case. Yes?
Can you explain how you got root 2 to the ground?
How do I got what? This thing?
No, root 2.
Root 2. Oh, this thing.
Yeah.
Yeah, what'll happen is, by the limit, okay, this is going to wind up looking like 1 over x squared. That's going to look like 1 over x. That's going to look like 1. Right? And the limit laws will get rid of these two. On that, does that make any sense or no?
Okay.
Basically, no? Okay.
No, again.
Okay, great, okay. When you end up doing this and you apply the limit laws at that, then you'll see that, yeah, you'll be left with the 2. All right. Again, if you want me to go through that with you, I'm happy to do that. Okay, let's think about this thing. The limit as x grows up of x squared plus x plus 1 over x plus 1. Okay, can we apply the quotient law? The answer with me is almost always no, right? Okay, because those limits don't exist. Both of these guys blow up. So no good. Don't be writing infinity over infinity. What would you do? Hint, what did we do last time? Divide by the highest power. Divide by the highest power in the denominator. What is that? X. Okay, so divide everybody top and bottom by x. Okay. Okay, now what happens? Again, we can't use the limit laws in this kind of form because what happens, this guy still doesn't exist, okay? This guy, this top guy blows up. Okay, so what can we do? Let's think about it instead. This bottom guy, you can use the limit laws here. What does this bottom guy approach? As x grows up, this guy disappears, and we're left with 1. So the bottom approaches 1. And yes, you can use the limit laws for that part. Up here, this guy disappears, this guy approaches 1, trivially, and this guy blows up. So the whole top blows up, okay? You can't use the limit laws for that, but you can think through it, and it's essentially the same kind of stuff, okay? As x grows up, and sort of outshines 1, and 1 over x disappears. Okay? Does that make sense? Okay. So there you go. You got something that blows up over 1. So the whole thing blows up. And as sketchy as that is, you can think about it that way. Okay? At least you're not breaking the rules. Does that make sense? Yes, ma'am.
So if this was on like a midterm,
Yeah.
you have to like write our thoughts on why.
You'd write something along those lines. Does that make sense? Yeah. So you do that kind of thing, or something equivalent, and then, yeah, you say the top does this, the bottom does this, therefore, yeah.
Get the answer like in the wrong way.
Say one more time, please.
What if you get the answer in the wrong way?
I have no idea. To be honest, if you just wrote infinity over infinity, would you know to write infinity?
Tell me why.
Yeah, right? Yeah, I don't know if you got the wrong answer, yeah, the right answer the wrong way, what I did. We'll think about it. Try to get it the right way. First rate advice there. Okay? Well, one other thing you could probably do is try to do polynomial long division, and then, you get the same kind of result. Okay, so you can do polynomial long division first and then process it. Does that make sense? Something that blows up over a constant is going to blow up. Okay? And incidentally, if that was minus x plus 1, you'd see a minus 1 there. That would approach minus 1, and this would be minus infinity. Okay. Okay. Let's do the picture. Hey, check it out. As promised, as we go to the right, the thing blows up. Okay? Which is what that says. And if you feel like trying, as you go left, it blows down. Okay, if I ask you for this thing, the limit as x approaches, quote unquote, approaches infinity, x plus 1 over x squared plus x plus 1, what would you think this is? It's the reciprocal of the other guy. What's going to happen? 0 is a good answer. And that makes sense, right? If that's going to blow up, then its reciprocal should disappear. Okay? It's going to be 0. How could we do this? Again, we could do our usual trick. We could divide through by the highest power in the denominator, which is x squared. So we get this. 1 plus 1 over x plus 1 over x squared. And this is nice, so the limit laws work for this one. Okay? That guy approaches 0, that guy approaches 0. So the top approaches 0. That guy approaches 1 trivially, that guy approaches 0, that guy approaches 0. So the bottom approaches 1. So by the limit laws, it's 0 over 1, which is very nice and well defined, and it's 0. Okay? All right? And again, that makes sense. And you remember at some point I said how higher degree polynomials beat the crap out of lower degree polynomials, possibly in different words, okay? Eventually, higher degree polynomials beat the crap out of lower degree polynomials, and that's exactly how, okay? They beat them badly, and that's how we talk about that kind of thing, okay? We don't say beat the crap out of, we say this kind of thing, okay? We say their ratio blows up, okay? And we talk about exponentials versus polynomials too, and we can talk about that later, okay? As a ratio, as a limit of a ratio. If you know about end behavior models, if you learned about this at some point, you could at least check your answer with that. So the end behavior model for this top guy, for those of you who know, is x squared. The end behavior model for this bottom guy is x. Okay, so this limit's actually just going to be the limit of x squared over x, or the limit of x, which is infinity, quote unquote. Okay, for those of you who've heard of end behavior models. If you want to know about that, I'll tell you about that. That's not kind of part of the course. Okay? Okay. All right, good. That's a special kind of blowing up. You've got enough weak asymptote, which we may talk about later. Okay, what other feature do we see in here? What other kind of asymptote do we see in here? Excellent. We've got a vertical asymptote. So let's quickly talk about that. I mentioned the end behavior model thing because it's a nice way of checking your answer. It's a nice way of thinking about these things, and if you like, I'll tell you about it. Okay, but this is the right way to do these questions. And that's the way we do in this course. Okay, so what do we see? We see an x plus 1 in the denominator. Okay, that's a hint that something wrong happens at minus 1. Okay, so let's look at what goes on at minus 1. Again, we see x plus 1 in the denominator, so something funky might happen at x equals minus 1. All right, let's approach minus 1 from beneath. X squared plus x plus 1 approaches what? Using the limit laws, it approaches 1 squared plus, that's supposed to be a plus, yeah. I did something, okay, good, yeah. It's minus 1, isn't it? Okay. Using the limit laws, or continuity, As x approaches minus 1 from beneath, this guy approaches minus 1 squared, which is 1, plus minus 1, so now 0, plus 1. So the whole thing approaches 1. Good? I have no idea if I've lost you all already. Okay. Okay, so the top approach is 1. What does the bottom approach? 0. Okay. The bottom approach is 0. But how does it approach 0? That matters. Okay, what does x plus 1 look like? It looks like that. As x approaches minus 1 from the left, as x approaches minus 1 from the left, that guy approaches 0 from beneath. Okay, through negative values, negative. Okay, write that however you want, right? Through negative values, from beneath, whatever. But you need to know. Okay, approaches 0 from beneath. Good? Okay, so as you approach, this guy divided by this guy is going to be negative, because you got a positive over a negative, so it's going to be negative. Okay, but this guy approaches 1 and the bottom approaches 0, so it's going to blow up or down. Okay, but because it's negative, it blows down. And that's the answer to the previous question, what do we do if? Okay, so the answer is, as x approaches minus 1 from beneath, this ratio blows down. Okay, again. We saw the x plus 1. That tells us something funny is going to happen at minus 1. Let's look at the limit as we approach from the left. Using the limit laws, we can see that the top approach is 1, just by plugging in, essentially. And we can see that the bottom approach is 0. Because the bottom approach is 0, we can't just use the limit laws for the whole thing. How does it approach 0? That matters, okay? If you've got the top approaching 1 and the bottom approaching 0, the whole thing's going to either blow up or blow down. To understand whether it blows up or blows down, you need to know what's going on as you approach. Since it's approaching through negative values, you're going to get 1 over negative values as you approach, so the thing's going to blow down, hence that minus sign. Does that make sense? Okay, excellent. So, x equals minus 1. The graph's going to do that kind of thing from the left, and ta-da, it does. Okay? Good? And you can do a similar thing as you come in from the right. Okay? As x approaches minus 1 from the right, you're going to get still this guy approaching 1. You're going to get this guy approaching 0 from above. So you're going to get through positive values. So it's going to blow up. Okay? So on that side, it blows up. And you can think about that separately. Ta-da. And that's exactly what that shows. Okay? So that's how you know if you should write plus infinity or minus infinity. Okay? Don't just use fake limit laws, divide by 0 and write infinity, because that doesn't work. Okay? And you might wonder, well, why don't we just do this kind of thing when we have, for all those other examples we did? We did examples like, you remember this thing again, this thing, that thing, this thing. Okay, those kinds of things and all their friends. Why didn't we think about it like this? Well, what happened there? We didn't have approaching some nice number over approaching 0. We had approaching 0 over approaching 0. We had approaching 0 over approaching 0. So that's why in those cases we didn't think like this. We did something else. We used a trick and then we used limit laws. Okay? Questions? All right. As h approaches 0, this guy approaches what? As x approaches 2, this guy approaches what? Okay, different deal. Even though both involve something that looks like a division by 0. Okay? All right, your other question was how do you do that breaking example in the assignment and similar things? For example, the limit as x approaches 3 of 2x plus the absolute value of 3 minus x. And once again, guys, please, if I make a mistake, let me know. Don't wait for me to catch it. Okay, so what do we do about this thing? This guy is essentially piecewise defined, right? Absolute values are piecewise defined. It's in two pieces, and the break, the transition, happens exactly at the place we want the limit. Okay? So when the transition in a piecewise defined thing happens exactly where we're looking for the limit, we need to look at one-sided limits. So that's the gimmick here. Okay, let's look at the absolute value of 3 minus x. Okay, that's just 3 minus x, where 3 minus x is non-negative, and it's minus 3 minus x if 3 minus x is negative. This is good. I should just use short shot because it's harder to break. Okay? And you can see this as x less than or equal to 3. And you can see this guy as x greater than 3. Okay? So essentially doing it on a case by you do it by cases. So let's come in from the left. Okay, come in from the left. So for x less than 3, we approach. Let's call this thing fx, so I don't have to keep doing this. F at x. Okay, what's that equal to? Okay, as we come in from the left, what does this look like? It looks like 2x plus, that case, 3 minus x. Okay? Approach from the left. 2x plus 3 minus x is just x plus 3. Okay, using the limit laws or later continuity, the answer is just 6. Limit laws do that step. Limit laws. All right? Yes, ma'am.
Would you have to do x approaches from the positive side?
Yes, ma'am. Yes, ma'am. So let's approach from the other side now. Because we want the two-sided one, right? So the left ain't good enough. Let's do both sides. Okay. On the other side, we have a slightly different story, right? We've got 2x plus that case. 2x minus 3 minus x. Okay? All right, what's that? Two x, so it's 3x minus 3. Okay. Using the limit laws, or later continuity, 3 times 3 minus 3. Let's look at that, it's 6 as well. Okay? Limit for both sides is 6. So the limit, the two-sided limit is 6. Okay? Why'd we do this? Because we had something that's piecewise defined, and we were looking at the limit as we approach the transition point, so we have to do it separately from both sides. If these two limits had disagreed, we'd say the limit does not exist. But they agree here, so the limit exists and has that value, as we see in this lovely picture here. And we go, well, why did we bother doing this? If we just plugged in 3 into this expression, we would have gotten the same thing. Yes, because it's continuous. Okay? And only because it's continuous. So we need to learn about that first. Does this make sense? Okay. I'll mention this again, the continuous thing. All right? Okay. All right. Two quick things. We mentioned this once, right? We mentioned Newton's law of cooling. We talked about exponential convergence. And I mentioned something without talking about limits. So let's look at limits. The limit of this temperature, you remember this is something that's placed in a medium that has fixed temperature, and it approaches the temperature of the medium over time. So as T grows, what's the limit of this guy? What's going to happen? You can use your limit laws. That's a constant. That's a constant. That guy, because K is positive, is going to shrink to 0. Okay? So the limit of this guy as little t grows up is 0. So this thing's going to disappear, and you're going to be left with that. Okay? Which is what we said back then. Okay? So you can write that using limits. You can say that the limit of big T as little t goes to infinity is TF. Okay? So TF is associated with the horizontal asymptote there. And a similar happens when a body is falling and there's actual drag. Okay? So the body accelerates until drag matches the force of gravity, and then you hit terminal velocity. Okay? And you might be able to model that as exponential convergence as well, if you're working back in. All right, this thing, and somehow I always leave 5 minutes for this. Let's do this again. I mentioned this last time, this cute name theorem. Suppose we want the limit of a function g as x approaches a. If we can pinch g between two other functions in this way, which is what that says, near a, such that the upper function and the lower function have the same limit L, that pinches g in near a, so that the limit of g as x approaches a must also be L. Literally what you see in the picture is what we're talking about, okay? Don't worry about all my talking. Okay? This also works for one-sided limits. This also works as x goes to infinity or x goes to minus infinity. And you can also play this game with sequences, though we're not going to do that. Okay. Where am I? Squeezing. Okay, what's the example I did last time? I wanted the limit as x approaches 0 of the x squared sine 1 over x. Okay, and we can't use the product law here because the limit as x approaches 0 of sine 1 over x does not exist. Okay, we did not see that. Okay, first of all, sine 1 over x is undefined at 0, obviously, because you have a division by 0, but it's worse than that, okay? There's a discontinuity here, and it's a crazy discontinuity we haven't seen before, okay? As we get closer and closer to 0, and these are higher magnifications, as we get closer and closer to 0, this guy oscillates. It oscillates faster and faster and faster, and we never actually get to a value as we approach 0. So this guy's discontinuous, so we can't just use the product law. What we can do is we can say that the sine, I did this last time, if you saw it, don't worry about it. Sines are bounded below by -1 and above by +1. Okay? For all x not equal to 0, obviously. Okay? That's how sines behave. For x non-zero, x squared is positive. So I'm welcome to multiply through by x squared, in case I said that wrong. For x non-zero, x squared is positive, so without having to flip any inequalities, I can just multiply through by x squared. Okay? Hey look, that thing that we cared about, we've now bounded by functions below it and function above it. Okay? Only near 0 matters, but here we've done it for all x, other than 0. Okay. The limit as x approaches 0 of this left guy, or the under guy, okay? You can use the limit laws to show that that's 0. The limit as x approaches 0 of the top guy plus x squared via the limit laws is 0. This guy approaches 0, this guy approaches 0, this guy is pinched in between. Okay? So while the limit of this guy doesn't exist, we can show that the limit of this guy is 0. Which is cool. There you go, okay? We pinched it in between those other two functions, and close to 0, we see it coming in towards 0, so the limit is 0, okay? Okay, I will quickly do this other example. Okay. This is a damped oscillator. So for instance, if you have a mass on a spring bouncing around and there's friction acting, okay? Friction takes energy out of the system. And you'd expect that as friction takes energy out of the system, eventually this mass would come to rest. Damped oscillator. Okay. So let's say the state or the position of this thing is given by A e to the minus kt cos omega t. Because we're cool and we like Greek letters. Where all those parameters are positive. A is the amplitude at 0. K is the damping coefficient. And omega, let's say, is the natural frequency. Or the angular frequency. Something to do with how this thing bounces around. K has to do with how friction takes energy out of this thing. And as you can see, as time goes on, okay, the oscillation gets damped. Okay? Because friction or whatever takes energy out of the system. Okay. You can see this thing has an envelope, right? We know that cos would just look like this, right? And A cos omega t would just look like this. But when we multiply by this guy, we get this sort of envelope. Really, really pretty. Okay? Does that make sense? Okay, so if it was just A cos omega t, we'd get a sort of constant amplitude thing. With this guy, we get a sort of amplitude that changes over time, according to that decaying exponential. So that's why the envelope does that. So, if I now wanted to know the limit as t grows of xt, we're very close, I promise. What would I do? We know that cos omega t, same trick as before. Cos is bounded below by 1 and above by plus 1. Okay? Because A is positive and e to the minus kt is positive, I can multiply through without having to change any inequality signs around. Okay? So again, what have we done? That function we cared about, we bounded it above and below by this, which is exactly the thing that forms the envelope. Okay? As t grows up, this guy decays to nothing. You can use the limit laws and that fact about decaying exponentials. This guy also decays to nothing. So once again, we've squeezed that guy in, this time as we go to infinity. We've squeezed this guy in, because it's bounded below by this and bounded above by this, and each of these guys goes to 0. This guy must go to 0. So that limit is 0. And in fact, friction takes energy out so much that in the long term, motion ceases. Okay? Motion dies away. And that's it for limits, guys. We'll talk about continuity next time. Thank you so much. I do squeeze theorem quickly, and I've done it quickly twice now, so I thought I'd go over something again, just to make sure this all made sense. Okay. I posted this a few hours ago. Okay, again, no questions, right? Okay. All right, so these are the two examples we did for the squeeze theorem. And these are the two limits we wanted to find out. And the problem, and the reason we can't just use the product law for limits here, is because that limit doesn't exist, and that limit doesn't exist, okay? I said a bunch of stuff about discontinuity last time. Pretend I didn't say that. Let's just talk about the limits not existing, okay? Does everybody buy the fact that these don't exist? Okay? This guy doesn't exist because you saw that function, it oscillates faster and faster and faster, right? Just between 0 and 1, sorry, between minus 1 and 1, okay? As you get closer and closer to 0, and so it's not approaching any one limiting value, okay? This guy, cos omega t, or cos, or whatever, as you go that way, it just keeps oscillating between minus 1 and 1, forever and ever, okay? It's never approaching a limiting value, so that limit doesn't exist either, okay? All right. So limits don't exist, so we can't use the product law for limits. So we have to do something else. And so what do? We take the sinusoids and we bound them, okay? And then we use something to sort of squeeze or suffocate them, okay? And there we go, that's it. So again, bound, squeeze, and this establishes that you're squeezing, okay? As you either squeeze like that or squeeze them as you approach A, and that way you can find that the limit is 0 in those cases. You guys have any questions about this? Yes?
It's for all sign, regardless of like what's inside, is always -1 and +1 as their max and min.
If the thing inside is something that limits your domain so much that you're not experiencing the whole range of sign, then no. Yes?
So you get my question, right? Like
For
sine
something
x.
sane, yeah, transformed sign? Yes,
Yeah.
a transformed sign will be b minus 1 and 1, yeah. A normal transformed sign. Yeah. Unless there's like an A outside. Yeah. Okay, yes?
Do we have to say that limit equals whatever by the squeeze theorem?
Say again?
Squeeze theorem to prove that-
Do you have to say squeeze theorem?
Yeah, like by the squeeze theorem, we have to indicate that.
I would, but if you just said all of this, that would be obvious to any reasonably intelligent grader that you're using the squeeze theorem. All right, questions about this? Anything unclear about this? Because again, everybody went quickly, and it's short anyway. Does it all make sense? That those limits don't exist, that we do the squeezing, and that that's the result we get in half. Yeah.
What is it not in between negative
What if it's not?
1? B or the.
Basically, you have to bound it between two things that do this. However you do it, it doesn't matter. As long as you can bound your function between two things that squeeze in or suffocate it or pinch it or something, right? It might not be between minus 1 and 1, right? Yeah. Question?
So the squeeze theorem will be on the midterm?
Potentially. Not necessarily kinetic.